So first we will do an application problem on Rankine cycle. In a Rankine cycle, steam leaves the boiler and enters the turbine at 4 megapascal and 400 degrees. The condenser pressure is 10 kilopascal. What we want to do is to find the cycle efficiency. Okay? Always when they give you such problem, as a first step, I advise you to draw the cycle on a diagram, on a TS diagram if you want. So here we have the 4 components of our cycle. So at the level of the boiler, we have heat addition to our fluid. At the turbine level, we have production of work, and this is the purpose of the cycle. So here, when they talk about efficiency of the cycle, we should divide the output, okay, over the input. You should pay attention that the output, you cannot say only that the output is W turbine out, because you are losing also power at the level of the pump. So the net, if you want, the net output is W turbine minus W pump. I'm talking in absolute values, of course. Or if you want, it's W turbine plus W pump. In case W pump is algebraic value, so W pump will be negative, W turbine will be positive. And when I do the balance, I will get the net output work produced by my system. And I will divide by the input. My input here is the heat provided at the boiler level. So in overall, my efficiency will be the net work over Qn. Okay? So always when you talk about efficiency, you should think, what is the purpose of my cycle? In the previous session, we have seen together refrigeration systems. In refrigeration systems, it's totally the opposite. So here we are providing heat to produce work. In case of refrigeration system, we are delivering work, electrical work to heat or cool. So in the other system, okay, when we calculate the efficiency, the output will be, if you want, the cooling or heating, okay, while the input is electrical power provided. And this is called, in case of refrigeration system, we talk about coefficient of performance instead of efficiency. Why? Because in general, when we talk about efficiency, efficiency is always lower than 100%. While when we talk about coefficient of performance in refrigeration system, COP can be larger than 1, okay? So this is why in refrigeration system we talk about coefficient of performance, while in these cycles, in Rankine cycles, we talk about efficiency. Okay. So now what we want to do is to calculate the efficiency of this cycle. So as we said, the first step, I will look at my inputs. What are the inputs that I have? I know that so just 1 second because the screen is black. Do you see the screen again? So the conditions I know here is the condition at. You see the screen?
Now,
Yes, now we see it.
Okay, okay. So at the inlet of the turbine, the conditions are 4 megapascal and 400 degrees, while the condenser pressure is 10 kilopascal. So this is just what I know, but it's enough to find the cycle efficiency. In order to know how to work, I should draw my diagram and put the conditions. So here we have a figure showing the conditions, okay? So I just know that at the boiler level, the pressure is 4 megapascal. At the condenser level, I have the pressure of 10 kilopascal. And I know that at inlet of my turbine, so point 3, this is the inlet turbine point, okay? So this is the inlet of my turbine and exit of boiler. And always in these cycles, in the boiler and condenser, I have constant pressure, okay? So 4 megapascal represents the pressure in the boiler. So whenever I am in a heat exchanger in general, we are working at constant pressure condition. So this is boiler pressure, and 10 kilopascal correspond to the condenser pressure. Now, as you can see here, we will see together that this information is enough to know the characteristics at the different points of our system. Why? Because once we know the conditions at point 3, okay, from 3 to 4, when we go over the turbine and over the pump, okay, we have constant entropy, constant S. So the first condition, then we can say that for point 4, I know now two properties. Point 4 is the inlet of my condenser. So for point 4, the pressure will be 10 kilopascal. And it is also characterized by another property that I can get from point 3, which is the entropy. So S4 is equal to S3. And we know that knowing two properties of a point is enough to determine all other properties. So now, using these two conditions at 4, P equal to 10 kilopascal and S4 equals to S3, I will be able to determine what is the enthalpy at point 4. Okay? Now, concerning point 1, I just, the first information I know is that it is at a pressure of 10 kilopascal. What is the second information I know about point 1 that will allow me to determine its enthalpy?
It's a saturated liquid.
Very good. I know the state of this point. It's a saturated liquid. So I will use this property to find the enthalpy at 1. Now, concerning point 2, I have two methods to determine the characteristics at point 2. The first method is to say that I know the pressure, okay? The pressure at point 2 is 4 megapascal. And the second property is what?
The specific volume.
The entropy, okay? Yes, the specific volume, I will talk about it as second method, okay? But if I want to just use the properties here, I can say that S2 is equal to S1, okay? So since S2 is equal to S1, and I know the pressure, I can find the properties of point 2. Just I want to tell you that point 2 is in compressed liquid zone, and sometimes in the tables, I will not find this point, the characteristics of this point. So in case I don't find in the compressed tables this S2 and this pressure to give me H of 0.2, I have another method which is relatively simple, that whenever I have a pump, we know that with the pump I have a liquid here. From 1 to 2, it's a liquid state. And in a liquid state, the specific volume will not change a lot. Okay, so whenever you have a compressed liquid, it is a good assumption to say that the specific volume in 1 is nearly equal to the specific volume in 2. Okay, because you know that for liquids, it's not easy to vary the density, and the density is it's inversely proportional to the specific volume. This is why, in general, when I go over the pump, I can say that nearly V1 is equal to V2. And in this way, I can say that the work given to the pump, okay, will be equal to V specific volume times delta P, okay? So knowing the difference in pressure and knowing the value of the specific volume at 1, I can determine the work of the pump from it. And then knowing the work of the pump, I can calculate the enthalpy at point 2. We will see in detail this in the calculation. Okay? So this is my general strategies to determine the different point conditions. And I need the different point conditions to calculate the efficiency. Why? Because what will be my efficiency? Who will tell me how to calculate the efficiency here?
Work turbine minus work pump over Qn.
Very good. So for the efficiency, I have, if you want, W net, which is W turbine. Again, I will tell you that it depends on the sign convention you are taking. If you are just finding W pump in absolute value, then you put here minus W pump. Other will consider that I will follow the convention of the equation in the course material. The equation in the course material will give me that omega pump is negative. This is why in this case I will put plus. So just follow one sign convention and you will get a good result. Okay, but don't mix. Yani, if you put here plus WP, pay attention that WP is negative. If you put minus WP, then you are taking the absolute value of the work. Okay, so you should always verify that the pump will take from the work of the turbine. Okay, so this is W net. When I add the algebraic values of the two, it is positive for WT will be positive, and WP will reduce WT because we need to provide work to the compressor over the input. The input is what is the heat added through the boiler. Okay, so this is Qn. Now, I can express the efficiency function of the enthalpies. How? So if I want to simplify this relation to give it function of the enthalpies, you know that W is what? It's m dot delta H. Okay? So for the turbine, W turbine, I can replace it by, so let me clear everything here. If I want to write W turbine, what is W turbine? It is m dot, which is the mass flow rate, okay, times what?
Times enthalpy.
Yes, which one? Which enthalpy? Look, at the inlet of the turbine, I have H3, okay? H3 is much higher than H4. Why? Because I will extract work from the turbine, okay? So the work will be m dot times the enthalpy at point 3 minus the enthalpy at point 4, okay? So it is m dot H3 minus H4, okay? Now, for the work of the pump, if I want to take the absolute value of it, so the absolute value of W pump will be equal to m dot times what? What enthalpies I will use to determine the pump
H1
work?
minus H2.
Very good. So here, look, if you are talking about the algebraic value, you do H1 minus H2. If you want to find the absolute value, you will take H2
minus H1.
minus H1 because H2 is higher than H1. Okay? So since I considered the absolute value, then it is H2 minus H1. And finally, what about the boiler heat? It can be computed from what? Qn equal to what? How can I find it?
MC.
It's m dot times what? Look, when I do MC delta T, okay, it's different. MC delta T is when you have change in phase, okay? Here, when going from 2 to 3, it's true that you have several phases. You have first variation in temperature, okay? Then you have change of phase. Then you have variation of temperature. So as you said, you can calculate it by dividing it into several steps. But in case you know the initial enthalpy and the final enthalpy, okay, no need to do that. So just, and plus I want to tell you something else. In general, we use MC delta T in case I have, let's say, a certain fluid at rest, okay? For a fluid at rest, it's different than a fluid in motion. When you have a fluid in motion, the heat will be affected also by if you want the velocity of motion. So it's m dot here. And I will just take into consideration the final enthalpy minus the initial enthalpy. In this way, I will consider the effect of internal energy change plus motion of the fluid. And if you have, if you went over the videos, we explained in detail that when you have a fluid moving, the variation of energy is m dot delta H. Why, if you have a closed system or you have if you have a fluid at rest, then the variation in energy is m dot delta U. Okay, so don't confuse both here. It's a moving fluid. Okay, so Qn can be computed as m dot H at point outlet, okay, minus H inlet. So it's m dot H3 minus H2. Okay. So as you can see here, if I replace in the equation of efficiency, what I will get the following. M dot will be simplified because I have it in all terms. Okay. So I can simplify it when writing here because I will have it in the upper and lower terms. So it will be simplified. Then the efficiency will be W turbine, which is H3 minus H4. And it is minus the absolute value of WP. So minus H2 plus H1. So here H3 minus H4 minus H2 plus H1 over H3 minus H2, which is from Qn. So over H3 minus H2. So if you want, as you can see here, the efficiency will depend on the four states because I have in my formula here H1, H2, H3, and H4. This is why to be able to compute my efficiency, I should determine the condition at the different points. Okay. So now I will start from point 3. For point 3, I know the conditions, 4 megapascal and 400 degrees. Okay, so since I know the Rankine cycle variation, I can say that point 3 is in the which region?
Superheated.
Very good, it's superheated. So when I go to the tables now, I will search in superheated steam and I will go to condition 4 megapascal, 400 degrees. So let us do this together. This is the superheated vapors, superheated vapor water. So as we said, it is 400 megapascal. So just let me check. Yes, sorry, 4 megapascal, 400 degrees. So 4 megapascal is 4,000 kilopascal. So here in this table, I have 8,000, 5,000, so it's just above. I am here. 4,000 kilopascal is 4 megapascal, and I want the temperature to be 400 degrees. So here, this is my condition, and H is, to check H is in which column? It is in the here. H no, here it's sorry. راحت التable يلا 1 minute. Okay, so I am here. It is the third column. Okay, so yes, that's it. So here I can read it. Here, the value is from the third column for 4 megapascal. The corresponding value of H is 3,213.51. So now I found the first value of H corresponding to 0.3. Okay. Now it's not enough for me because for point 3, what should I select also? So I need from point 3 not only H, what also? Let us go back to the figure. I need to get S of 3 because I will need S of 3 to determine the condition at point 4. Okay, so let us check together what will be the value of S4. So for S4 here, I go to my table. S is given by this column, the first one. Okay, so the first column represents S. Then I will go back to 400 degrees and 4 megapascal, so I can read the value of S. Okay, this is the value. So the value of S will be 6.7689. Okay, and always pay attention for your units. So the unit here is, you can see it here, H and S. H is in kilojoule per kilogram and S is in kilojoule per kilogram Kelvin. Okay, so now once I got the value of S from this table, this will be equal to S at point 4. Okay, so let us keep it in mind. S is 6.7689. So now I will try to search for this S for a value of pressure equal to what? So it's nearly 6.77. Okay, 6.77, and I want to go to a pressure now of 10 kilopascal. So I expect that 0.4 will be between, it is saturated state. Okay, it is a mixture at 0.4, and it is characterized by S equal to 6.77 and the pressure of 10 kilopascal. So I will go now to my tables again, and now I will go to saturated tables, not superheated one. And I will try to search for a pressure of 10 kilopascal. So here I will go to pressure entry table. So here I have 10 kilopascal, as you can see here. Okay, and I will search for values of S, and my value should be between, okay, between S saturated liquid and S saturated vapor. So it is the case as expected. Okay, because as you can see here, S saturated liquid is 0.65 nearly, while S saturated vapor is 8.15, and I am interested to find the point corresponding to S. My S is 0.677. So in order to find the quality at my point, all I have to do is to write that. I can write it here. So S at point 4 will be equal to S of saturated liquid, SF, plus the quality X times SFG. SFG represents S saturated vapor minus S saturated liquid. So here you can just calculate it by doing 8.1501 minus 0.6492. But because it's widely used, okay, they directly give it in SFG. Okay, so here you can say that this will allow me to calculate X. So X is simply calculated by doing S4 minus SF over SFG. So just I will now replace the numbers that I have. S4 is 0.677. SF is 0.6492. I think the value we have found together is 6.77, not 0.677. Yes.
Yes.
Yes, it's 6 point. Yes, let me fix it. بتعرفوا كيف عرفت مثلا هون أنا؟ كيف عرفت إنه 0.6 مش كتير منطقية؟
No, it's too close to saturated liquid.
Yes, it's too close to saturated liquid. While I expect in the Rankine cycle, the value is close to the saturated vapor. Okay, so here if you made بالغلط a certain error, you can directly see this in your calculation. Okay, so just let us fix it here. So it is 6.77. Okay, so 6.77 minus 0.6492 over SFG, which is 7.501. So I get now the quality X. Once I have the quality X, I can now determine what is H at 0.4. Okay, so to get H at 0.4, all I need is to get from my table the value of HF at this pressure, which is 191.81, and HFG, and now I can say that H at 0.4 is equal to HF, which is 191.81, plus X, which is calculated, okay, times HFG, which is 2392.82. And in this way, I completely defined my point. I got the value of H at 0.4. Okay, now the next step is to compute. So here, now for 0.1, to get H1, as we said, okay, 0.1 is characterized by saturated liquid state. Okay, so at 0.1 I have the saturated liquid state. So I can go now to my graph and just I select HF. Okay, I already found it, HF at 10 kilopascal. So HF at 10 kilopascal is the value of H1. And finally, just for H2, okay, for H2, as we said, we can say we can write in two ways. We can say that to get H at 0.2, I can go to compressed liquid tables, okay, and put the condition that for 0.2 I have S1 equal S2 and the pressure is 4 megapascal. Or if I have the work done at between 1 and 2, how can I find the work done between 1 and 2? Who can tell me? I don't have it. They didn't give me the work. But how can I find it?
V delta P.
Yes, I can find it by V delta P. Okay. And then, so I have the value at point V at 1, I can calculate it. Okay. I say that the work that should be given to the pump should be equal to V delta P, and V delta P is equal to an absolute value to H2 minus H1. This will give me directly the value of H2. Or I should go to tables. Okay, so in general, when you have a pump, this is easier for you. You can do it instead of going to tables. So just I need the specific volume at 0.1. So to get the specific volume at 0.1, I go back to my tables. As you can see here, you have in your saturated tables, you have two sets of tables. In one set, you have the entropy and enthalpy. So here we will use it just to find H1 from here. This is H1. And now to get the value of S at 0.1, V at 0.1, sorry, I will go back to the other set of tables, which will give me the specific volume. As you can see here, I have the specific volume and the internal energy. Okay, so for the specific volume, I will go to 10 kilopascals, and I can read here the corresponding value of specific volume, and I can say that this value is common between 0.1 and 0.2. Okay, so now let us see together the details of calculation.
MS.
Yes.
The two methods don't lead to the same H, right?
But it will be close, no?
Okay. Yeah.
It will be close, yes. Sometimes it will not lead to the exact same value, but it will not be so far. Yani it is a good approximation.
Okay.
Okay. So if you do both, I will consider it right. But sometimes, why we use this method? لأنه sometimes بالtables of compressed liquid في states ما بنلاقيهم. So this will be an alternative for you. Okay. So now, as we said, they will do the same procedure we are doing. So first, they started from the pump. Okay. As we said, for the pump, we can write that the work of the pump. Here they take the work of the pump as absolute value. Okay. So I repeat, it depends on the convention you are taking. Just from the sign, you should understand, yani, when you write H2 minus H1, you expect to get a positive value because you know that at the exit of pump, H2 is higher than H1. So if you are following the convention that work is negative when given to the system, then when you want to calculate W, you put H1 minus H2. If you just want to find the absolute value and then replace, when you want to find the network, do W turbine minus WP, then you put H2 minus H2, okay? So H2 minus H1 will be equal to the absolute value of work delivered to the pump, which is the specific volume times delta P, okay? P2 minus P1. P1 and P2 are given. The specific volume at point 1 is considered to be equal to point 2 since we are working in the compressed liquid state and we don't have a high variation. In general, if the value of V to change, we need a very high variation in pressure. So if the pressure will change a lot, because if you look at your table here, you can see from your table that V is nearly not changing a lot. To have a high change in V, you need a very high delta. The change in pressure should be significant. Okay. So this is why it's a good approximation to assume that the specific volume is constant. Okay. So in this way, I can calculate WP, and from WP, I get the value of H2. Okay, so we are done with H2. Now they moved then to calculate the condition for the turbine exit. So we know for the inlet state, since P3 and T3 are known, as we did together, they calculated H3 and S3. So these are the values we found together. Then by setting S3 equal to S4, they got the quality. And as you can see, the quality is closer to the saturated vapor state than the saturated liquid state. So you are nearly at 82% vapor and 18% liquid. Okay, and once you get the quality, you can replace the quality into the formula of enthalpy to get the value of H4. Then knowing H4, now we can calculate the turbine output. So by doing H3 minus H4, here all your calculation will be per mass flow rate. The unit is kilojoule per kilogram. Okay, so since they didn't give us m dot, no, I don't need it because I can calculate the work per unit flow rate, and then when I put the efficiency, anyway m dot is simplified and I don't need it in my problem. Okay, so now as you can see, W net will be computed as WT minus WP because they consider WP as the absolute value. So they calculated the work delivered to the compressor, they consider it as positive. This is why they put here minus WP. So once you get W net, you just still need the Q inlet, which is at the boiler level. So now at the boiler level, to find Q inlet, Q into your system, it is H3 minus H2. So now all you have to do is to calculate. Already you